Acyl chlorides and acid anhydrides are both more reactive than carboxylic acids. In both molecules, electron density is pulled away from the delta positive carbon of the carbonyl group, making the carbon more open to attack by a nucleophile. In addition, both the chlorine and the carboxylate group make good leaving groups because, once left, the ions are stable, either in the form of a chloride ion or in the form of the carboxylate ion. Both molecules react with a wide range of nucleophiles at room temperature, often in the presence of a base, and as such they're widely used in organic synthesis. The mechanism for these reactions is nucleophilic acyl substitution, which neatly breaks down into step 1, addition of a nucleophile to the delta positive carbon, and step 2, elimination of the leaving group. Let's have a look at this in a little more detail. Firstly, with water as our nucleophile. So, uses the lone pair of electrons on the oxygen to attack the delta positive carbon, and we can make way for an extra bond by the electrons from the double bond moving up onto the oxygen. In our first intermediate, we can see that the oxygen that took on the electrons from the double bond has now got a negative charge, and the nucleophile, in this case water, the oxygen, is positively charged because it's now making 3 bonds. It's used up one of its lone pairs to make this new oxygen-carbon bond. In step 2, the oxygen retrieves its lone pair by kicking out the proton and keeping the electrons from the oxygen-hydrogen bond. So we can see in the second intermediate that water has become an OH group, and in the final step the double bond is restored, and at the same time the chlorine atom leaves as a chloride ion, taking both the electrons out of the carbon-chlorine bond. And the final product of this reaction is a carboxylic acid. You'll notice that although the previous steps were reversible, this final step isn't, because the chloride ion is a better leaving group than the hydroxide ion. Our byproduct is HCl. Let's look at this mechanism with an alcohol as the nucleophile. Once again, the oxygen from the OH group uses its lone pair of electrons to make a new bond to the delta positive carbon, and the electrons from the carbonyl double bond move on to the oxygen. In step 2, the oxygen retrieves its lone pair by kicking out a proton. This second step is facilitated by the presence of a weak base such as triethyl amine, a nitrogen with 3 ethyl groups bonded to it. Because nitrogen can use its lone pair to attack the proton or help remove the proton, while the oxygen takes the electrons out of the oxygen-hydrogen bond. In the next step, the double bond is reinstated and the chloride ion leaves. And finally, we're left with an ester, plus once again a byproduct of hydrogen chloride, HCl. Moving on to look at this reaction with ammonia as a nucleophile. The nitrogen in ammonia has a lone pair of electrons. It can use that to attack the delta positive carbon, and electrons from the double bond move on to the oxygen. The nitrogen is now positively charged in our first intermediate because it's making 4 bonds, and in exactly the same way as oxygen did in the previous 2 examples, we are going to see the electrons from the nitrogen-hydrogen bond return to the nitrogen as a lone pair. However, the ammonia has 2 roles in this mechanism. Firstly, as a nucleophile, using its lone pair of electrons to form a new carbon-nitrogen bond, but secondly, as a base, with the ammonia being used to abstract the hydrogen from this intermediate. This has an effect on the byproducts of the reaction. And finally, we see the double bond between the carbon and oxygen restored, and the chlorine leaves as a chloride group, and we're left with an amide, in this case a primary amide, because the nitrogen has still got 2 bonds to hydrogen. Now, in terms of our byproduct, between our intermediates we didn't just lose hydrogen. What we actually lost was an ammonium ion, because if you remember, ammonia was used as a base to help remove the proton from the first intermediate, which means that our byproduct is not HCl in this case, but it is ammonium chloride, NH4 plus Cl minus. We need to be clear on that when we're writing an overall equation for this reaction. And we're going to look at this mechanism one more time, this time using a primary amine, methylamine, as our nucleophile. I've drawn it out so that we can see the lone pair of electrons on the nitrogen, tap delta positive carbon, electrons from the double bond move on to the oxygen. Once again, amines are weak bases, so we have our amine behaving as a nucleophile but also as a base in this second step. So if I were to write this out the other way round, then we can see that the lone pair of electrons on the nitrogen, when it's behaving as a base, come in to attack this proton, and the nitrogen-hydrogen bond breaks, with the electrons staying on the nitrogen as our lone pair. So at this stage, it's not just a proton that's leaving, but the CH3NH3 plus ion. And in the final step, we know what's going to happen. We'll restore the carbon-oxygen double bond. The chlorine leaves as a chloride ion, taking the electrons out of the bond, and we end up again with an amide, this time a secondary amide because our nitrogen is only bonded to 1 hydrogen. And again, our byproduct is going to be CH3 NH3 plus Cl minus, so the chloride salt of that amine. And last but not least, let's look at this nucleophilic acyl substitution mechanism with an acid anhydride. The reaction, the mechanism is exactly the same. So I'm just going to run through it with water as a nucleophile. So lone pair of electrons on the oxygen attacking the delta positive carbon, and electrons from the double bond moving up onto the oxygen. Our first intermediate, exactly the same. Oxygen is positively charged because it's making 3 bonds, but it's going to restore its lone pair by losing that proton. So we can write minus H plus between our 2 intermediates. In the next step, we are going to have the carbonyl bond restored, with the oxygen using that pair of electrons making up the negatively charged. And this time, instead of a chlorine leaving as our leaving group, we've got the carboxylate ion leaving as the leaving group. Our final product is a carboxylic acid, in this case ethanoic acid, as is our byproduct. Because in our last step, we lost a carboxylate ion, in this case the ethanoate ion. You can find the notes that accompany this video, as well as some practice questions and answers and all sorts of other really useful stuff at Crunch Chemistry. There's a link in the blurb below.